Hi folks, and welcome back to Math with Captain Rod. I'm making this video here to be a conceptual video to describe what electric potential is. So right now, what I'd like you to do is ignore all of this stuff. This is just stuff I'm going to reference a little bit later, and just kind of hyper-focus on this. So imagine we got a charge here of amount what I put plus Q here. And for the sake of this discussion, we're going to imagine it's nailed down. It can't go anywhere. Put a nail in it there. Now, some things that I hope we know. If we brought another charge into this region, these two charges would repel one another. The force on this charge would be up and right. Now, I'm going to remove this for a moment. What causes that force is what we call an electric field. This particle produces around it an electric field that points radially outward. If I pick a point in space here, like right here, the electric field direction would look something like this. And I wrote some equations over here about this stuff. So this is how the electric field for a point charge is calculated. KQ over R squared. This R hat here, that's just a direction. It means basically radially outward. The electric field is radially outward if it's a positive charge creating it. Radially inward if it's a negative charge creating it. Now if I put this particle back to that position, okay, the electric field around this charge acts on this one, creating a force which would be in this direction. So this force is what we call the Coulomb force. Now that same force acts on this particle down and left. I don't really need it for the discussion because I'm going to talk about just this one, so I'm going to get rid of it. And the Coulomb force is directly proportional to the two charges involved and falls off with distance squared. This is referred to as Coulomb's law. K, it's usually written Q1, Q2 over R squared. I chose to use like a big Q and a little q for this discussion. If this particle were now allowed to leave, it would accelerate away in this direction. Now if we plot this force, like what it looks like, as the distance gets bigger and bigger, as this particle moves away, the force gets smaller and smaller. So I'll kind of model that here. So as this thing kind of moves in this direction, this force decreases in magnitude, gets smaller and smaller and smaller according to this, basically. Now, as this particle leaves, this force eventually goes to zero. You notice it's got this 1 over R squared behavior, and as R gets really, really big, this expression gets really, really small. Right now, a very important concept from physics is work. Now, work is force times distance. When the force is varying with the distance, however, it becomes a bit of a math problem. On this graph here, the work done is this area here under this curve, which I'm highlighting in green. I even wrote down here, work done by this force is equal to this green area. And that is equal to some positive number. Now, for conservative forces, the work done by the conservative force is always equal to the opposite of the change in potential energy of the system. So that work done in this, which is represented by this green area under the curve, is equal to minus PE2 minus PE1. Now, because the force goes to zero at R equals infinity, and so does the electric field, and so does what's called the electric potential, by the way, it's very custom to say that the potential energy is zero at R equals infinity. Also, the electric potential is zero at R goes to infinity. So long story short, this term is generally considered to be zero. So the work term, which is represented by this green area here, is equal to the potential energy when this charge is at this location. Now, I could actually put that charge anywhere on a circle. And as long as I'm the same distance from this charge, I would have the same potential energy term. And here's where the electric potential comes in. Right? It's important to realize that, imagine that this charge were larger, like I multiplied it by 2. I'm just going to get rid of this here. That would make this curve higher, the green area bigger, more work done, and a higher potential energy. Well, electric potential is a property of space, and because of that, this charge is divided out. So here's what electric potential is. Electric potential, which is defined as potential energy per unit charge, in this example would equal this green work done with this charge divided out. So it's a number that has units of joules per coulomb, and that number would be the same anywhere on this circle. So for example, let's say the electric potential on this circle ended up to be 2 joules per coulomb, and I'm just making up a number. That means that if I put 1 coulomb of charge right here, it'll have a potential energy of 2 joules. If I put it here, the potential energy also 2 joules, also 2 joules, also 2 joules, also 2 joules. I could put that 1 coulomb of charge anywhere on this circle. In reality, it's not a circle, it's a sphere. Oops. It's like a 3-dimensional surface. I could put this charge, or a 1 coulomb charge, anywhere on the surface of the sphere, and it would have a potential energy of 2 joules. Again, just a made-up example. Now, if we start closer to the surface, or to the inward charge here, right? If we start at a smaller value of R, right? If R is smaller, the force is larger, and basically what that would do is we'd be starting, oops, let me get rid of this, with a smaller value of R, so we'd be starting here on the curve, and we would have more total area under the curve. Therefore, if the particle was released from this inner surface, as it leaves, the Coulomb force would do more work on it, as represented by this green area, and therefore the potential energy of that particle would be higher on the inner surface than it would be if it started at the outer surface. Therefore, this surface is at a higher potential than this surface. And in general here, as I get closer and closer and closer to this charge, we're at a higher and higher and higher potential. So let me try to summarize this. This video is getting a little long and a little more involved than I meant it to be. So what is electric potential? It's defined as potential energy per unit charge. So it's a number that has units of joules per coulomb. It's effectively the work that will be done on a particle of charge Q if you release it from any position. It's the work done as this particle accelerates away to infinity with this charge divided out. Right? And that's why it has numbers of joules per coulomb. Now the electric potential is a property of space. Right? So in this picture here, everywhere on this circle is at the same potential. I move inward, everywhere on this circle is at the same potential. I'm going to draw one more. We move even further yet. Everywhere on this circle is at equal potential. Right? The electric potential increases when you move against the electric fields. So remember that this charged particle, it creates electric fields which are this way, radially outward. Anytime you move up into the field, you're moving towards higher potential. Anytime you're moving with the field, you're moving towards lower potential. So anyway, that's my description of conceptually what electric potential is. It's potential energy per unit charge, which is equal to this green area here, divided by the charge of a particle. It's a property of space around charged particles that tells you something about potential energies. So hope that this video helps. Have a great day.